This is the origin, evolution, and exploration of planetary crusts. And, this was an idea that, a group of us came up with. And rather than having, a petrology, a remote sensing, a geology session, we decided it'd be best to try to integrate all these approaches. And again, as I mentioned in my talk earlier, survey provides us this sorts of opportunity for sample people to talk to modelers, to talk to remote sensing people, and putting together a more coherent product or understanding based on that integration. Today's first talk is given by Lars Borg, and the title of that is An Age Constraint on the Giant Impact from Lunar Sample Chronology. And for the speakers, we're going to give you 12 minutes. We're going to be really liberal, give you 12 minutes, and I'm going to, or Lars over here is going to raise 3 fingers when you should kind of tidy up your talk, and then everything after 12 minutes you're cutting into your questions. So Lars,
Thank you. It's nice to be here and to give a talk on chronology that's full of a session that's not populated by chronologists, because most of the time we eat our young. And so hopefully we can look at a broader picture here. And to that end, I'm going to try and fly at a relatively high elevation and not delve in too much to the details, and talk generally about the conclusions that have come out of the work that I've been doing for about 10 years with various groups. So the premise of this talk is that we can get some age constraints on the giant impacts if we know the solidification age of the moon. And if you look on the, let me see, whoops, sorry. If you look on the left part of the diagram here, basically this is the idea that the time of the giant impact equals the duration of accretion plus the duration of cooling plus the age of solidification. And that's essentially illustrated on this diagram here, where the moon formed as a result of a giant impact, forming a debris ring. The debris accretes, forming the moon itself. The heat of accretion results in temperature increases, causing melting in the moon, and eventually the moon solidifies, forming a series of primary reservoirs, which we're trying to constrain the age of by looking at the samples. So what I'm going to do and focus today on is the chronology constraints we have on the solidification of the moon based on isotopic analysis of samples. And to that end, I'm not going to focus on the nits and grits of the actual analyses themselves, but rather paint a broad picture of research that's been done by dozens of people that I've been working with over the years. So in order to understand the significance of the chronology, we have to have some general model or picture in our minds for the evolution of the moon. And this is presented on this diagram over here. And this is a sort of a generic magma ocean model of lunar evolution. And this has been deduced not from chronology, but rather from observations such as the widespread occurrence of anorthosites on the lunar surface, the composition of those anorthosites, the presence of incompatible element-enriched material, as well as experimental investigations determined on basaltic rocks. The model itself is illustrated in this cartoon here. The idea, again, is after accretion, you end up with a moon that's either completely molten or partially molten. As it cools, it solidifies. The mafic minerals form at the bottom of the magma ocean. Felsic minerals, most notably anorthositic plagioclase, rises to the surface. As solidification continues, the last thing that solidifies is represented on this diagram here, something called ore creep, which is composed of incompatible elements that are enriched in all the components that haven't gone into the minerals that crystallized before them. Then the final idea of lunar crustal evolution is that there's a series of rocks, genetically called the MG suite, that are intruded into this lunar crust. So to constrain the age of solidification, these are essentially the materials that we have to work with that can give us a time estimate for when the moon might have solidified. So to just go through these one by one, this is the final diagram I showed you on the previous slide, giving a hypothetical and idealized cross-section of the moon today. The upper crust is composed of phron anorthosites, represented here. Ore creep is these late-stage incompatible element-enriched material, which is thought to be in the upper mantle. Mafic cumulates are represented here, and these are, in fact, the source regions from which the Mare basalts are derived. So ages of these materials come from the Mare basalts themselves. And then we can get a minimum age of solidification of the Moon based on ages of these intrusive rocks. And there's a couple of types. One is called the Magnesium Suite, and the other is called the Alkali Suite. So going into the literature and just doing a very quick summary of the ages that have been determined over the last 40 years or so, you can see that there's a large range of ages of these reservoirs, and the range is so large that it doesn't really provide any firm constraints on the primary solidification of the Moon itself. And this is illustrated here. The age of the published range of ages for phrononorthosites goes from 4.3 to 4.56. Mare basalt source regions ages go from 4.3 to 4.4. Ore creep has been modeled to go from age of 4.3 to 4.5. The Alkali Suite, which is dated primarily by zircons. You saw a very excellent talk by David Kring yesterday, who showed a large range of spectra that they've generated. The same spectra shows up if you look at all the literature data, and ranges from about 3.8 billion years to about 4.42 billion years. And then the Magnesium Suite has ages that go from 4.1 billion years to the onset of the formation of the solar system. And again, these age ranges are so large that it really offers no constraints on the crystallization age of the Moon. However, if you look at the ages in detail, you realize that not all ages are equal. Some ages are more reliable than others. And I've tried to illustrate this on this diagram, where I've made a compilation of all the ages that have been reported for lunar crustal rocks. So one of the things to keep in mind as an audience who does not perhaps focus solely on samples is that even though we have a lot of samples, there's very few lunar materials that are suitable for chronology. And this essentially is a complete list of analyses that have been done over the last 40 years. On the upper end are rocks from the Magnesium Suite. Down below here are rocks from the phrononorthosite suite. 2 points to note. First of all is that from a chronologic standpoint, these rocks range in age by about 200 million years, 250 million years actually. And second of all, individual age determinations on particular samples often don't agree. Many of these samples have very ancient ages, but there's also usually an age that's been generated on the same sample that's significantly younger, making the interpretation quite complex. The problem stems from the fact that when you do chronology, oftentimes these rocks are amenable to the application of only one chronometer to the system. And as a result, if that chronometer is in error, you don't have a secondary chance to check that with a new chronometer. So in the last 5 or 6 years, our analytical techniques have become good enough that we can now start applying multiple chronometers, to individual samples. And we've gone back and dated 6 of these samples over the last 5 or 6 years. And each of these samples was chosen in part because it had isotopic evidence that it was ancient. So the samples that my group has redated are represented by the blue dots here. All these ages have been determined by multiple systems. The systems that we're most care about are the samarium neodymium system. There's 2 chronometers. We use the lutetium hafnium system, lead, and occasionally we're able to apply the rubidium strontium system to these rocks. All of these yield concordant ages by at least 2 and sometimes as many as 4 different isotopic systems. So we have a lot of faith in these. Point to note here is that in many cases, these old ages are not reproduced. The second point to note is that all the ages that we have determined, both from the Magnesium Suite and the phrononorthosite suite, are essentially concordant at about 4.35 billion years. And this is a quite robust conclusion, in part because all of these samples have been dated using a short-lived system that would show obvious evidence if there was significant amounts of the radiogenic isotope produced, and we just simply don't see it. So although these ages have uncertainties associated with them, the one thing we're very confident in is that these rocks are not old. Another group of rock we can date, and again, Dave Pring showed some of this, are ages determined for Alkali Suite based on spot analysis by ion microprobe of individual zircon grains. You can see this is the range of all the data that were reported in the literature as of a couple of years ago. Something like 480 analyses, individual spots. There's a peak of ages at 4.34, which is concordant with the ages that we're determining on the MG suite and the ferroanorthosites. There's a tailing of ages down here to about 3.9, 3.8 billion years, which is generally interpreted to reflect resetting of the zircon mineralogy as a result of impacts. There's also a shoulder here of older ages. This is a little bit deceiving because most of these analyses, in fact 41 analyses of one mineral grain, are represented in this shoulder here. If you just consider the oldest few grains there, this becomes a fairly precipitous drop-off. Having said that, there are certainly ages, 5 or 6 individual spots or zircons that are older than 4.34 billion years. The vast majority are at 4.34. Another way we can obtain ages is using model ages. This is an example of a lutetium hafnium model age. This is the age of an individual sample. This is the hafnium isotopic composition. Both these are parameters determined from mineral isochrons. All these samples have been dated multiple times, so we have confidence in these ages. This is an evolution line for chondritic evolution. The age of which these source regions of these materials form is defined by the intersection of a line regressed through the data points with the model growth curve. For lutetium hafnium, the age is 4.35 billion years. Again, in agreement with the other ages. This is an analogous plot for samarium neodymium. There's more data points here because samarium neodymium is more prevalent in the literature. Nevertheless, the age that is obtained from the intersection of the regress line through the model line is 4.39 billion years, and again, is concordant with the other systems. The final type of chronology I'd like to show you has to do with the formation age of Mare basalt source regions. This is an isochron plot of samarium neodymium of Mare basalt source regions against the neodymium isotopic composition measured in the basalts themselves. The line regressed through this is proportional to the age of the sample. In this particular case, it has a slope corresponding to an age of 4.33 billion years. This is our data. This data set has been reproduced by 4 or 5 other people. We're just sort of the last people to the game here. But we all agree that the age of these samples is somewhere in the 4.35 billion years, concordant with the other ages. Very importantly here, however, I've also plotted the mineral separates that we've analyzed for various ferroanorthosites, represented in the blue colors, and magnesium sweet rocks. I guess they're also represented in blue colors here. The point to note here is that all these data fall along a single isochron with a slope of 4.3 billion years. You can look at the isotopic compositions of these, and what it means is that these rocks are derived from a common source region at the same time. The composition of that source region can be estimated on a TI diagram represented by the slide on the left here. This is evolution of chondritic neodymium through time. This is based on an isochron we determined on a CAI. This is, you can see that we're close to reproducing the terrestrial value, so this is likely to represent evolution of neodymium in the Earth-Moon system. If you look at the isotopic composition of the lunar rocks that we've determined based on this isochron, it lies on the intersection of this line at 4.33 billion years ago. What that ultimately means is that all these rocks appear to be derived from an undifferentiated source region at 4.33 billion years. So complicated models that require resurfacing, remelting, and reequilibration of the moon become very difficult to reconcile with these types of observations. So in the final slide I'd like to show you basically illustrates all the range of ages that we've determined from these various things. Ferroanorthosite ages we get are 4.34 billion years. Ages for the Urocrete, average of the two, are 4.37 billion years. Magnesium cumulates, average of 4.34 billion years. Magnesium sweet rocks, 4.33 billion years. Alkali sweet rocks defined by the peak and zircon ages are 4.34 billion years. All these ages are concordant within the resolution of our chronometers. And this is what we would predict if all these products were primary solidification products of a magma ocean. So, in conclusion, most of the chronologic evidence for the moon is consistent with a solidification age of 4.34 billion years with 30-40 million years uncertainty. This is based on the analysis of all the materials I've showed you, which include the Froen northicites, Mare basalt source regions, Ur creep, magnesium sweet rock, and most of the alkali sweet rocks. All the samples are derived from reservoirs with the same neodymium isotopic composition, and that reservoir is similar to the best estimates of undifferentiated material, again, consistent with magma ocean solidification. This implies that the giant impact must have occurred late in solar system history, or that accretion of the moon after impact was very slow, or that the magma ocean remained molten for a long period of time. The simplest estimation for the rate of accretion and cooling of the magma ocean is about 50 million years. So a ballpark estimate for the giant impact is about 4.4 billion years. Thank you.
Thanks, Lars. And we have time for two more questions, just two questions, quick questions. Carly. And you're the next talk, so we're going to take time off. Sit down.
I noticed in your list of samples for your fans, they were all from Apollo 16 except for a meteorite. Is that, I'm thinking the links to the geology, is that special about Apollo 16, or is it that everything else is messed up that we got at basins?
Yeah, I guess I'll speak in the mic, but I mean, that's where the fans are from in the collections. You know, there aren't very many in the Mare basalt sites. And so, I mean, we went to 16 site to get Highlands material, and that's the Highlands material we have. But your point is well taken. It's a very limited data set.
Okay, quick question, Lars. Jim Head, Brown University. Just, is another option for your options at the end there to explain things, large impact melt sheets and differentiation to explain some of the ages, younger ages of the orthosites, crystallization ages?
You can come up with more complicated models. There's no doubt about it. The main problem, as you rightly allude to, is the age of the Froen and orthosites. If you have any sort of overturn or interaction, subsequent re-equilibration, you have to somehow involve the anorthosites in that. So if in the sense of having anorthositic melt sheets and things like that, all being related to a late impact, yes, but it gets progressively more complicated because all these materials have to also have re-equilibrated with the material in the mantle, with the material in the creep and whatnot to maintain the neodymium isotopes.
Yep, I see. Thanks.
Thank you, Lars. And now she has only 10 minutes.